Okay, all right. So good afternoon, everybody. Okay, it's okay. So good afternoon. So apologies first for the slight delay this seminar because of important business in the morning. So we are really very grateful to have Professor Matthew Turner visit to our department. And he's been kept very busy in the past 3 days. And we are very fortunate to have him staying on to have a scientific session this afternoon. So just a brief introduction to Professor Matthew Turner. So he has a very distinguished scientific career. He had long association with the Cambridge University, where he did his undergraduate study and PhD. So when he was an undergraduate student, he was already the president of the Trinity College, I presume. That was the college you were affiliated with. Yes. Yeah. And then because of his exceptional performance, so in 1991, he was elected a fellow of the Trinity College. And he did his PhD in theoretical soft condensed matter physics in Cambridge, supervised by Professor Michael Cates, who's now a Lucasian professor there. And in case you don't know, that chair was held by Isaac Newton and many other very distinguished physicists. And during that period, he was working on the dynamics of polymers that can exchange mass and started his professional career in soft matter physics. And then he moved on to do a postdoc with Jean-François Joanny in Strasbourg, France, another very distinguished soft matter physicist. And there he developed models of polymeric liquid crystals. And then he briefly spent some time at the University of California, Santa Barbara, his KITP, very famous institute, on a series of membranes on the Royal Society University Research Fellowship from Cambridge. And then after that, he joined Warwick University as a faculty member. And I don't know how he did it, but and then at the same time taking up the WM Keck Fellowship in the Center for Studies in Physics and Biology at Rockefeller University from 1998 to 2001. And I know probably that was the period when they first set up this interdisciplinary program with Eric Sijer and many other distinguished scientists. So it was during that period he moved into biology and worked on protein DNA interactions. And he continued his research at the interface between physics and biology on the Julia Curie Visiting Fellowship at the prestigious ESPCI Paris, very distinguished institution. I just looked up on Wikipedia this morning. And also the Marion Rothschild Visiting Professorship at the Institute Curie in Paris. And in 2010, he won an excellent leadership fellowship. And then in the last 3 years, he spent much of his time in Japan. A sabbatical is funded by a fellowship from the Japan Society for the Promotion of Science and the Leverhulme Trust, and has been working on some completely new problems in both collective motion and the interface between mathematical epidemiology and economics. That's something he's going to tell us this afternoon. So this morning, welcome Professor Matthew Turner.
Hello, everyone. It's really a pleasure to be here. I've had the opportunity to take a look at in closer detail at your physics department over the last few days. That's sort of my day job, so to speak, while I've been here. And I must say, it's a really inspiring department. We're very lucky to be students or staff at this department. Okay, so what I'm going to tell you about today is one of those completely new things that Leihan mentioned in his introduction. And I guess, like many people, we started to think a little bit about epidemics during the COVID period. And we've got, I think, a few new things to say, not only about epidemics, but also about ways of looking at control theory problems in economics. So the sort of last line of my title, I guess, is that the really new thing here, where we've been taking inspiration from physics-informed machine learning, which is sort of quite a new field now in machine learning, where the idea is that you encode the laws of physics into the learning problem. So rather than just black box trying to mimic something, you say it's a physics problem. Turns out you can do the same kinds of things in control theory, because there's very close relations between control theory and physics. And in particular, you can even do it when you've got a Nash equilibrium in this control theoretic problem. And I suppose what we've been thinking about is how you could use a neural network to mimic what's called an objective function, or in economics often a utility. It's like what your preferences are, why you're sitting in this lecture, and you balance the things you like against the things you don't like. And it's kind of a secret formula. And it's not obvious to anyone, even often to the individuals concerned, what that secret formula is. But you reveal it through your behavior, through what you do. So the sort of central idea here is we could observe your behavior and infer what your hidden preferences are. So that's sort of the jumping to the final there, but we'll work there gently. So this work's been done with three colleagues in Japan, Ryuichi Yamamoto, John Molina, who are both in Kyoto, and Simon Schneider, who's just moved to Tokyo. So I learned one kanji, or two kanji anyway. So this I really like, the combination, of course, is opportunity and danger here, being crisis. And I think possibly one could think of the same thing about epidemics. I mean, it's at one point, it's also dangerous, but at least for scientists, it's an opportunity to think about these problems maybe in greater depth. So I just wanted to put up one slide telling you what else I'm doing, because, if any of you are interested in any of these other things, we could discuss afterwards. And this is going to be very pictorial. So one of the things I'm interested in is membranes, is understanding them from a theoretical perspective. And this is a cartoon of a cell, the inside of a cell, and all the bits in the cell are bounded by phospholipid bilayer membranes. And actually, mathematically, these are nice structures because they're two-dimensional sheets, and they're quite simple to describe. You can write down the energy and forces, things like that, and really solve problems. And here's a cartoon of one of the problems we solved recently, which is when you take a membrane protein. It's obviously a highly stylized cartoon of a membrane protein called KVAP here in pink. And I've inserted it into a lipid bilayer. These are meant to be the phospholipid molecules here. And what this protein in particular does is it anchors into the membrane in a way that's not symmetric. It basically introduces some kind of bending in the membrane. And then we want to know how these things move around in the membrane. That's actually a very interesting field, because we've got a two-dimensional fluid here, but the two-dimensional fluid is not flat. So the mathematics you need for this sort of thing are actually quite reminiscent of the kind of mathematics you use in general relativity. When you have a non-flat space-time, you need to use the same kind of differential geometry to calculate the fluid flows in these problems. And we were very lucky that there was an experimental lab actually doing measurements on the diffusion of these proteins. And they had some data they didn't understand. And basically, by doing the proper fluid dynamics in this kind of curved environment, we were able to contribute to that problem. Then second field I just want to mention, which I think is kind of fun, is something we call the topological glass. And you might have come across this if you've ever tried to pull a rubber band out of a bucket of other rubber bands. So you take a really long rubber band, put them in a bucket, shake them up, and you put your hand in and you grab one and you try and pull it out. Is it going to come out? Probably not, right? Because it's tangled up with all the other rubber bands. And even, however hard you pull, eventually maybe you'll get all of the rubber bands that come out of the box all together. But that's kind of interesting from a topology perspective, because none of these rubber bands are actually linked in any sense with the other rubber bands. We know that because they're rubber bands. You could separate them. And the physics would actually be very different if I cut all the rubber bands first. Every single rubber band, first I cut it, then I put it in the box and I shake it up. Now I can take one rubber band and it'll slither out by one end very easily. So the topology here is creating a state that we think is extremely similar to a glass, the kind of glasses you find in physics. It's a jammed state. And it's jammed because of the propensity of these rubber bands to interpenetrate and form a large interlinked network. And that large interlinked network can have relaxation times that are exponential in the length of the polymer. So the longer the polymer you make, the longer it takes you to unentangle it. And this has a lot of characters that are quite similar to the kinds of transitions we see in physics, where you see glass transitions. And because I'm in China, I want to just give you another example of these topological glasses. A student at the time, who's actually Italian, decided it would be a good idea to make this stuff out of pasta, noodles, if you like. So he rolled out a sheet of noodle material, joined it over and sealed the join, and then he cut it in such a way that you get these rings. And then by cooking it, boiling it up, and then you put it on your plate and you take your chopsticks or your fork, you pick it up, it's impossible to eat because you can't get one off the plate. You have to pull the whole thing up. So I actually have a published pasta recipe. I'm very proud of this. And finally, another thing I just want to mention that we're interested in the moment, perhaps this is actually the main area of my research at the moment, is thinking about collective motion. So this is meant to be, I don't know if you see it at the back, it's meant to be a picture of a large flock of birds, a kind of bird that in English is called a starling. I'm not sure you have it on. And you can get hundreds of thousands of these birds live together. And when you see a movie of them moving, it's a really remarkable fluid. It's a huge amorphous mass that's nonetheless very, very clearly defined at the edge. You know, there's an inside where all the birds are and an edge at an outside. This thing moves, seemingly of its own volition. And it's a kind of material made up of individuals, a bit like fluids made up of atoms in physics. But these atoms are driven, they can fly. And we've been asking questions about how you might build models of systems like this, in particular, coming kind of bottom up, asking, you know, rather than taking an off-the-shelf physics model and plonking it down on top of this problem and saying, well, these look a bit like spins to me, I visited it, well, I'll build a spin model. That's not a very good idea, because birds are not spins. So we've come bottom up and we've said, well, what's happening here? What's the information that the birds are receiving? They're receiving some image of what they see around them. So visual sensory input is a key element. And then what are they doing? Well, we've got a candidate algorithm that we're very excited about. So we think it has much wider application, in fact, than just in bird systems. In fact, it probably applies in complex games like chess. And the idea here is that you want to keep your options open. When you play a game of chess, when you lose the game of chess, the feeling is that your options to make moves become increasingly limited because you have no freedom, you have to react to the opponent. That's a signature of losing, not only at a game of chess, but a game of life. What you want to do in life is you always want to have many options open to you, both as scientists or students, but also as living animals. You want to gather food, that gives you options. You want to avoid being eaten by a predator, that gives you options. So it turns out this kind of principle can be applied to models in these systems, I think with great promise, and probably lots of other problems where you have evolved systems that are targeting fitness in an uncertain world. So I'm afraid I don't have, that's a completely different talk. I don't really have time to tell you much about it, but I think it's a lot of fun. So today I'm going to try and focus, on mathematical models, essentially, of epidemics. And really we're motivated by the question of how would you make good decisions in an epidemic? And that is both from a personal perspective, but also from a controls perspective. Because governments in China and also in Europe had a huge problem what to do with COVID. And I think often, as very true in Europe, but probably also in China, you know, political decisions were made that were not based, perhaps, on mathematical optimization. And it would be nice to know if there's a way of solving this problem kind of optimally in a control theory sense. So we're going to make a few simplifying assumptions because we have to. And for those of you that know about epidemics, I'm going to tell you a lot more about this later. The kind of model we're going to use is called an SIR model, and that divides the whole population into susceptible people who haven't yet caught the disease, infected people who've got it right now, and recovered people who've had the disease but have recovered from it. We're also going to make an assumption that's very kind of central to economics. You can criticize it legitimately here, but we're going to make it anyway, which is that agents are rational. That means they do what's best for themselves. They can compute what they should do, and they do it. So what that means is that both individuals and governments have this thing that I called an objective function, which is a function that gives you a score. Basically, you can't decide between doing A and B. You look at the score of doing A and B, and you compare them, and whichever one gives you the best score, that's the one you do. We're also interested in this case, I'll explain it a little bit later, where you've got essentially selfish individuals. If you want what an individual in society is doing when there's a disease in society, there's two things. You could be all going around, we could all be going around thinking, I'm going to do what's best for society. You know, I'm going to sacrifice my own interests in order to promote society's interests. That's probably not very realistic in most countries, certainly not Europe. So what people do is they do what's best for themselves. And you can get a solution where what's best for yourself becomes a self-fulfilling prophecy because everybody's doing it. And the whole society ends up adopting this strategy where nobody can benefit by doing any more, by doing anything else. And in economics, that's called a Nash equilibrium. I might say a bit more about that later. One of the things we wanted to look at, because it seemed to us to have a lot of political consequences, was the role of healthcare thresholds. So at least in the UK, I think one of the things that politicians were really looking at is that things change if more than about 1% of the population have this disease at any one time, because the hospitals are overwhelmed. So basically, from a personal perspective, that means the cost of you getting infected rises from something we call alpha 0, that's just a number, a cost, you can think of it in pounds or dollars, to another number if the proportion infected is higher than this threshold. The number of the proportion of the population infected are greater than this thing I call IHC, that's HC for healthcare. And that because if you catch the disease, you might not have a hospital bed. And broadly speaking, that makes it twice as likely that you'll die of the disease. So the cost sort of roughly doubles at that point. The other thing that can happen is governments can intervene here. They can tell you what to do. And in this economic model, the way we're going to kind of put that in is through a monetary incentive or a tax. Basically, the government will incentivize you to do things that it thinks is good for you to do. And a key point maybe here is that individuals in governments can have different interests, potentially. And then in the sort of second part of the talk, I'm going to talk about these Nash Neural Networks. And as I already hinted to you, what we're going to do is use these as a way of learning these objective functions of individuals. This is how you develop the score, how you decide what to do, from what you do. So that's an inverse problem. It's a complicated inverse problem. It's not obvious it has a solution, actually. I'll show you one example where it does have a solution. And this objective function, which is just a mathematical function, it takes as input the state of the system and gives it an output, a score. We're going to approximate that using a neural network. And for those of you who care or know, there's all sorts of tricks going around in computer science at the moment involving this magical package JAX that allows you to take a derivative, like in calculus TDX, through computer code. And this is actually an amazing tool. Okay. So this is just an introductory slide showing you what happened in the disease very early on. And things were very different in different countries, essentially. It wasn't so good. It wasn't so good in Europe, maybe better in Vietnam. This is a log scale. So why were these countries so very different? You know, in Vietnam, you've got 10 to the -3. I think this is cases per 100,000 population against the 5 order of magnitude higher in the US and France. So of course, it could be because the disease was different in these countries. Maybe also detection and reporting was different, and resources because you don't have healthcare. But these two things we think are really important. I mean, first of all, what the government's telling you to do, but a key aspect here is what the individual population members are choosing to do. So I'll come back to that very soon. But first, let me give you a little cartoon of this SIR model I mentioned earlier. Here's a population of people, and all the susceptible people I've colored in blue. Something comes along, I don't know what it was, maybe it's a bat or something, and that infects the first person, and that person passes on the infection. You get a lot of red people occurring. And then the first recovered happens. The first individual to catch it, they become recovered. I color that person in grey. And then this disease sweeps through the population. And eventually, at the end, you'll just have susceptible people and recovered people. And all the infectious people have recovered, at least in an SIR model. I know that's not quite what's happened in COVID. Right. So, of course, there's lots of other ways, just to tell you, there's lots of other ways of building these models, these what are called compartmental models. The thing I told you is you go from susceptible to infected to recovered. It's a mean field model, which means that we treat the population as a kind of well-mixed, a mixture of typical individuals who are all essentially the same. And then we just follow the proportion in each of the compartments. You can do lots more, right? You can have other compartments. You can say between being susceptible and infectious, you've got an exposed category. Or you can take account directly of the people who died and haven't recovered. Maybe the recovered people can become susceptible again. There's all sorts of things you can do. You can also go much more in-depth than just mean field models. You can look at contact networks. So maybe I know who's friends with whom, and I can follow that through society in time and space. But we're not going to do that. We're going to keep it really simple. And one of the parameters that you might all know about, I suspect you all do, is this basic reproduction number. So I'm going to have sort of two notations. Typically, at least in the West, this is called R0. But we're often going to use this notation. I'm going to call it cat star. Sorry for the redundancy, but that's how it is. And the number here is typically we're going to use is 4. And if you look at the variants that were floating around earlier on in the epidemic, 4 is probably about right. Some were a bit higher, some were a bit lower. And just to note that there are other diseases that have got R that's much higher. So what this R number means is it means one infected person in a sea of other people who are susceptible, so the disease has not yet progressed very far, will infect 4 other people. So this will obviously lead to exponential growth, 1 to 4 to 16 to 64 and so on. And here's the mathematics. Apologies, but there's going to have to be a little. You write down basically 3 differential equations that tell you what happens to the proportion of the susceptible, infected, and recovered. And the top equation tells me how the susceptibles are changing in time. It's the rate of change of the proportion of susceptibles. The susceptibles are going down because they're getting infected. So you start off with a proportion of susceptibles essentially 1, and the minus sign tells you that it's decreasing. It's decreasing at a rate that's proportional to this rate constant I told you about R0. That tells you how fast it is happening. But it also requires an infected to come into contact with a susceptible. So those of you who know about chemical rate equations, for example, this is very similar to a chemical rate equation where one molecule bumps into another and causes a reaction. That's exactly what happens in SIR. One I bumps into an S and passes on the disease. So that's basically where this equation comes from. And then the infected, well, for every susceptible that becomes infected on your balance sheet, you have to have a plus R0 IF, because these guys are coming over here, and that's how the infecteds change. But they're also recovering. So the proportion of infected, so the minus here, I, in general, you could have a time scale here. You might have it divided by a time scale, but we've set that time scale to 1. And then the recovered, not that we actually care about them in the mathematics, they're just simply the balance sheet entry for the infecteds that are coming out of here, well, they're going into recovered. So you can solve these equations with some initial conditions, and typically you might say, well, there's a very few, only not very, very small individuals who've got this right at the beginning, maybe one person, and everybody else is susceptible, and there's no recurrence. And you solve these equations numerically, and here I've chosen R03 for some reason. And what happens? Well, right at the beginning, there's almost no infections, so there's almost no catching the disease. But actually, this is exponential growth. It's just starting from a very small number. And you really see the exponential start to cut in here. So at this point, the infections are going up really rapidly, and they're still being passed on exponentially. Each individual is passing it on, well, in this case, to 3 others. So the susceptibles start to fall because everybody's catching the disease. And then eventually, I mean, everybody's at this point around the peak. You know, lots of people have already caught the disease. There aren't many susceptibles around anymore to catch it. And then eventually the disease dies out completely. And what you see is that there's still some people left over as susceptible who haven't caught the disease. So the idea, one of the essential ideas in this problem is to keep this blue line as high as possible, to make as few people as possible catch the disease. In other words, as many people as possible go through without having caught the disease. So that's the sort of game. And you can think of the terminology that was used in the West as herd immunity. And if you look at the equations, I can rewrite the I equation by pulling out this common factor of I can pull it out. And then I can see when the proportion of infected stops rising. It stops rising when this term in brackets is 0, because then the infections aren't going up anymore. And in particular, when this term is 0, the infections can stop growing. But the best you can hope for, actually, if you solve that equation, I've done it down here, is that the susceptibles could be as many as 1 over R0. So you can, in principle, retain that fraction of people who haven't caught the disease under this model. But the problem is that you can also get a lot less than that. And in particular here, if I look at a third, that's about there, well, this is almost exactly at the time where the most number of people have caught the disease. It's not the time when everybody stops catching the disease and there aren't any infections anymore. It's the peak of the infection. So this is a very bad strategy because lots more people are catching the disease than need to because you haven't controlled it. You've just let it sweep through the population. Right, so that black line is basically well above the blue line, and that's bad. You don't want that. Right, so there's all sorts of things you can do. You can change the probability of death depending on how many infecteds there are. As I told you, like there could be a healthcare capacity threshold here, and you've got more chance of dying above it than you have below. And these sort of sketches here are just meant to show you that if you control this by hand, so imagine you were kind of magical and you could control everybody's behavior. And what you're going to do is you're going to keep everybody's behavior at a level where the disease is hardly passed on. And then eventually, when you think it's safe to do so, you let people come back to their normal behavior. So what happens is, like, if you look down here at the infected, you know, you're keeping everybody under control, everything below the healthcare threshold here, and you start to ease off, well, boom, you get another peak. So all this is trying to indicate is that you can't do these things by hand. If you just cook up an idea like this and you implement it, you're likely to get it wrong. You're probably going to develop something like this. We have mathematics. Mathematics is our friend. We can calculate how to do this properly, so let's do it. But first, this talk is really all about spontaneous behavior. So this is some data from Denmark, and it's around the time of the first confirmed case, about here on this graph. And what Denmark did is it told everybody needs to stay at home because you can't go out anymore because it's dangerous to the disease. And that happened around here. So what you see is that everybody stopped going out, right? I mean, the government told them not to go out. So retail and recreation dropped. People weren't going to retail anymore because they were told not to. Nobody went to the train station anymore. They didn't go to the grocery so much. They actually went to parks a bit more and stayed at home a bit more, didn't go to work. So that's exactly what you'd expect if the government told you to stay to lock down, and you did it. But if you look in Sweden, a similar first confirmed case today, no lockdown. The government said you do whatever you like. What happened? Well, exactly the same things happened, actually. People stopped going to the shops. They stopped buying groceries. They go to the park a bit more. They didn't go to work, and they certainly didn't go on a train. They did it spontaneously. They decided that that was the best thing for them to do, so they did it. This effect is basically not included in any epidemiological models, or very few, right out in the fringes of the field. But it's quite important because it means that, this Arnold parameter, it's not sealed in stone, right? It's something that people can play with. Right. So here's the sort of clever bit, if you like, of what we're doing in terms of the Nash equilibrium, is that you've got a population, a whole bunch of people, and in a more compact form, I've written exactly the same equations I had before. I'm just using a dot for a time derivative. And now I'm replacing the Arnold thing by something I'm calling K, and I'm using K for the population infectivity. So this is related to the behavior of the population. And I'm saying we're all individuals, and we have a slightly different set of equations. We are concerned not with what's going on in the population, but what our probability of being susceptible is, and what our probability of being infected is into the future, as we look into the future. And these equations are a little bit different to these equations. Why? Well, first of all, they depend on our own behavior, not that of the population. We can decide whether we're going to go out or not. You catch the disease from the reservoir of the population. If you need to have an idea, it's only when you bump into an infected person that you catch the disease. But you'll catch it if you yourself are susceptible. So it's kind of a mixture between the population activity and your activity. And similarly for the probability of you being infected, it's the opposite balance sheet entry. If you become infected, you stop being susceptible and become infected, and you recover. So these two equations, what we do is we say, well, actually, the individual is subject to the population behavior. If I magically fix this, if I fix A, and we knew what it was, we could work out what we wanted to do over here with kappa. But actually, at the end of the day, we're going to say the population is just a sum of individuals. So at the end of the day, we're going to set kappa equal to K. Ooh, did I write that on this slide? I don't think I did. But we're going to do that. But you can't do it at line 1. It's kind of subtle but important. You can't just say, well, kappa is going to be equal to K, so these equations are the same. PS is going to be the same as S, PI is going to be the same as I, because everybody's the same. You just throw this equation away and just deal with that one. You get a different kind of equilibrium. This is actually kind of deep, actually. Right. So I'm going to tell you a bit about optimal decision making, and if I see slides with lots of equations on, I think this might be one of them. I might zip through them a bit quickly. So I talked a bit about this utility or objective function. So in a very abstract way, you can think of it as encoding your preferences, and you can think of it as a score. You could have it in units of dollars, for example, and it assigns an outcome, a utility, depending on what the state of the system is. Equity, so to generally imagine this is something that tells you about the state of the system, not only now but into the future, because you care about catching the disease not just today but tomorrow, and what you do. So, and what you do is you look to see which one's the best outcome, and then you decide on a behavior that selects the best outcome. And this is something you see very much in control theory as well, where you have an evolution of the state of the system. In physics, you could think of this as a one-dimensional position of a mass. Depends on some equations. This big F is Newton's force in physics. Okay, X something like X dot equals AT, I guess, if you're accelerating. But in epidemiology, it looks a bit different because we've got these other equations, these SI equations. They're going to go in here. So this is going to be the line where we're going to find out what's the disease conditional on what we do. And in my model, what we do is how infected we are. Whether we go to work, which means we risk being infected, but we get to go to work, or not. And the utility looks something like this. It's the integral of some function over time. So you care not just about getting the disease today, T0, but you care about it on some finite time window, maybe an infinite time window. And then because I'm chopping it off here, maybe I just need to put a little cleanup term here. Anything I miss from TF to infinity, I just put it here. This is a detail, you can forget about this. It's basically the time integral of some function. The question is, what should that function look like? Well, of course, we don't know what that looks like, but I'm going to give you, right, not right now, but I'm going to give you on the next slide, I think, our theory of what that might be. So here's the formulation. You know, you've got the equations of SIR dynamics, you've got a utility, and you're going to choose the R max A, you choose the action that maximizes your utility. And for those of you that know and care, you don't have to worry about this if it doesn't mean anything to you. You can write this down in extremely physics language. You can write down something that looks like a Hamiltonian. I've even called it H, which is something that encodes this top function L, and something that's like a set of Lagrange multipliers to make sure that your equations of motion are satisfied. Right, so then you've got some equations. Well, just kind of trivially, you want the derivative of H with respect to these Lagrange variables to yield the equations of motion. But you've also got other equations that are quite familiar in physics. They're called in economics, they're called the co-state equations, that tell you conditions on what these Lagrange multipliers need to be. And if you care about it, things related to the boundary condition. I'm not going to care about that so much. And this one is the most important one. It's optimal control. It basically says you want a maximum in the score when varying over the actions. Right, so with these are our fancy equations. And that's what we're going to do. And then at the end of the day, we're going to set K equal to kappa. That's, I think, what I told you. Right. So next bit of the kind of setup of this problem, you can have people like Boris Johnson, who is no longer our leader, who might have different preferences, who might select incentives to bias what we do, right? Boris tells me I'll give you money if you don't go to work, so I don't go to work. And you've got two levels of problem here. You've got individuals in population who are deciding what they want to do in the disease. Also, they have to decide they're given incentives. The government wants to know what's going to happen down here if they give you certain kinds of incentives. Right, so here's an example, in fact, it's the typical example of what we choose with a subjective function. So we really don't know what it is in the population, but this, for me, as a physicist, this looks reasonable. So, right, this utility, my score for a set of actions, what does it depend on? Well, first thing, you might have what's called in economics discounting. For a physicist, you normally write this as e to the minus t over tau. It's some kernel that tells you that how much you care about the future decays. I don't care about my future in 100 years' time, because I'm going to be dead. So I don't know what my decay rate is. Maybe it's a year or months, I don't know, but it's often we're going to actually completely ignore this, but in principle, it should be there. Now, here's the kind of important bits. The first bit is you've got a cost of catching the disease that depends on how likely it is you've got the disease, or probability of being infected. This is the key control parameter, right? You say to yourself, it's going to cost me $1,000 if I catch COVID. And of course, that depends on the individual, but we're going to imagine there's a typical cost that a typical individual could assign to catching this disease. And we're going to put it in here. I've made it a function of I because, as I told you before, maybe it costs you more to catch this disease if all the hospitals are full than if they. Okay. The second term is something that tells you about the cost of reducing social activity. So this is your behaviour, this is how infectious you are, and this is the background infectivity of disease that we're. So if your behaviour corresponds to the background infectivity, it's like you didn't know there was a disease. You're going about your average daily business, and the disease is progressing as if you didn't even know it was there. And probably with common cold, that's exactly what happens. So you're not making any behavioural modifications. So if kappa is equal to kappa star, this term vanishes, no cost of behavioural modification, because you're not making any behavioural modification. And this naturally selects an equilibrium, the case when you have the diseases infected. And then maybe you've got a term here which says the government can offer you incentives to bias your behaviour away from what you do naturally. It pays you some money to stay at home. Okay, and this bit, we really don't care about it. It's just because I've chopped off this upper limit. In all the simulations I'll show you, this is completely negligible. Right. So I told you about these equations. I told you about this. I don't know why I have this slide. What about this? I think we can probably skip this one too. Yep. What about this one? Yeah, let's skip that as well. Right. Okay. Right. So basically, I told you that this Nash equilibrium, and our control theory here gives us a control equation for kappa, and we can compute it, and then we're going to set equal to k. So basically, this is what you get when you take the derivative of that Hamiltonian. You get something that's quite complicated. It depends on these Lagrange multipliers that are time dependent. S is the function time, I is the function time, and the government inspection. But in principle, you know what all these things are, you know what your behavior is going to be. And you can solve all of this numerically. So we actually have an analytic solution in one case that I'll show you. It's actually on this first slide of results. And for everything else, we have to solve it on a computer. Right. So I'm showing you three curves here. This is what you're doing. Are you infectious or not? This is what you're how many susceptible there are in population to fraction, and the same thing for infectious. And this is time coming along here in disease generations, seeing them as weeks. So the baseline is the grey line, and you can see what I've done here just by hand. So I said nobody does anything, the behaviour stays at 4. In that case, the susceptible, well, the infections go up and very rapidly, lots of people catch the disease and it drops down to 0. You get a very sharp drop in infected and a low level here of people who haven't caught the disease. This is a bad solution because few people have not caught the disease. Many people have caught the disease. And then you can solve these equations in two cases. One, where you say, right, I'm going to forget about this idea I told you where individuals and population are different. I'm just, at line 1, I'm going to set them the same. I'm not going to worry about this Nash argument. I'm going to say we're all heathens, if you like, and we all do exactly the right thing for society. This is called the utilitarian solution. And if you optimize that, you get this gold line. So what happens is you get a lot. The best solution is one in which you've got lots of people who don't catch the disease. And I should say here, of course, we have to parameterize all this. We've chosen a cost of 400 against the distancing cost of 1. So that means it costs you basically 400 times as much to catch the disease as it does for you to substantially modify your behavior for 1 week. Right. Then the other solution you can do, and you can see that the black dots for our analytic solution are on the numerical code, that's nice. You can solve it for the Nash case. So this is the case where you do treat the individuals and the population separate. You first say, work out what the individuals should do, and then you say in general, and then you say, I'm going to set the individual population behavior the same, and you solve it. You get a different trajectory. It's actually quite remarkable when you think about it. And what that says, if you're a selfish individual, you should behave a bit differently. You should drop your behavior a little bit earlier, and you should come out of it a little bit slower. And what that means is that, in fact, the susceptibles drop more slowly, but it's not quite as good as the utilitarian solution because, you know, this is below the gold line. And remember, we want to keep this final susceptible as high as possible. So the fact that you've allowed people to cheat a bit means that society is a little bit less worse off. So everybody's a bit worse off, but individually, they're doing the best possible for themselves. So these are things you see in game theory, actually, quite often, and it's appearing here. And of course, the profile of the infected is also very different. The Nash solution actually drops the peak quite a lot. So that says people's spontaneous behavior will result in a reduced peak. That's exactly what we saw in the behavioral data from Sweden, so it's kind of consistent. But funnily enough, actually the best of society is kind of to get a peak out of the way a bit early on and then surf out on this tail so that you end up with a very high number of susceptibles in late times who haven't caught disease. Right. So I'm telling you here a bit about Nash equilibrium, and I'm telling you what happens when you have different costs associated with catching the disease. And you can see things change a bit. So this is control, this is your behavior. These are the optimal solutions. So I've solved the control theory problem. And as I turn up the cost of the disease, well, what happens? With low disease cost, all you do is you just drop your behavior a little bit early on and then you just forget about it. You make the disease a little bit more costly, well, you drop your behavior more and then you forget about it. Really costly, you drop it and then you stay low for a long time. But what you see over here is actually quite interesting, that that results in a large change in the peak of the infectious profile, right? So at low cost, you don't care, the disease just sweeps through. At moderate cost, you see a big peak. At high cost, everybody's super cautious about the disease and you get this very broad profile. And here I've showed you a few things about the infection and the total recovered. I think I'm going to, in time, just a time, I'm going to speed on from that. You can do the same thing with the threshold for healthcare. So I told you about that. So this might be a constant healthcare cost, the black line here, high healthcare costs. The grey line is low healthcare cost. This green line is what happens when it's low if nobody else has caught disease, but high if the hospitals are full. So we're interested in that, and that appears in our utility in this high dependence of the cost of catching the disease. It basically goes up when the hospitals are full. So let's see what that does, and that's actually kind of interesting. So this is the infection cost I just showed you on the previous slide, and I'm turning it up. So first, there's two values here that are where there's no difference. The grey line's down the bottom, and 100 unit cost. The black line's at the top, that's 200 unit cost, so it's more costly. And they'll get somewhere in between. Down here it's low cost, over here it's high cost. So what you might expect is you might expect that the curve for the overall low cost for the what you do and who's infected might be between the green line, might be between the grey and the black. Because over here, the green line is between the grey and black in terms of infection cost. But what you see is actually the green line is outside either the grey or the black, both for the control and for the infected. So what you get out of introducing a healthcare threshold like this is that you get stronger behaviour, even though the overall cost is lower. Introducing a switch like this actually gives you stronger response in the population. Basically, people don't want to exceed the healthcare threshold because there's a sudden increase in cost, even though the overall cost is lower. So that's interesting. People will spontaneously target healthcare thresholds in their behaviour. That's optimal, because all of this is optimal control. I think I'm going to skip that slide. Maybe talk a bit about government decision making. Right, governments can have different incentives, I told you, and they can put this epsilon in, and then we just solve the problem, just like I told you before. So we've got individuals who constitute a population and governments informing them. So now we've got two control theoretic problems. We've got the individual utility. Individuals are choosing a behavior kappa, their behavior, but maximizes this. And I should be very clear, this kappa is a function of time. I'm not emphasizing it really sufficiently on a slide. You're choosing your behavior today and into the future. Are you going to go to work next week? And the government, they've also got an objective function, and we're going to, for simplicity's sake, we're going to build it in the same way that the individual does, because it encodes the essential features. There's a cost to the government, this is the subscript G, of people catching the disease. There's a cost to the government of people not going to work, and the government can give you money. Right, so if the government gives you money, there's a balance sheet entry on the government objective function. It costs them to give you money. It's not efficient for people to send people checks to stay at home, but they're willing to do it because it gives them control over the disease. And that government incentive appears in your utility as well. You get a payoff if you change your disease. And assuming that everybody's talking in Nash equilibrium, which we're going to assume, and the government puts in an incentive epsilon, you can work out what the population will do. It will do this. And then what you do, what's kind of a bit new here, is you have to simultaneously apply control theory at both levels of this hierarchy. You say the government has to apply a control theoretic problem to a control theoretic substrate, which consists of people optimizing a utility. That gives you two sets of coupled Hamilton equations that you can solve. And here's what you get. So this becomes a bit busy, but let me talk you through it. So again, I'm showing you behavior intervention now, susceptible to infected as a function of time. I've got the baseline still, which is nobody does anything. Everybody's behaving just like they normally would. And that gives you a sharp drop in susceptibles in the 50s. And now you've got a few other things going on. These are the curves I showed you earlier with no government intervention, the Nash solution, these are the same, and the utilitarian solution. And now I give you what happens if the government can intervene. If the government can intervene, and this balance sheet factor on the government is zero, that means the governments can intervene for free. There's no cost of the governments of intervening. But what that means is that the government immediately targets the utilitarian solution. Right? I've aligned the government's utility and the individual utility. The governments can do anything they like for free. Well, they know what the solution is. You want to target the society-wide optimum solution. That's the gold line. That's what we would have targeted if we'd been bees and ants. But things change if the government, it's actually costly for the government to intervene. If sending checks for everybody is a costly operation, the optimal solution shifts because that government control theory problem now has a cost associated with it, and you get different results both for the behavior, the intervention, the susceptible, and the infected. So basically, our punchline here is that if you want to solve this problem, and of course it's a highly stylized framework, but at least we can make some progress, you really need to know you need to couple the government decision making to the individual decision making, and you need to know whether government intervention is costly or not and how costly it is. Right. Okay, so you can also look at what happens. This is the curves I showed you earlier. What happens at various infection costs to the infection profile. It's logarithmic above this level and linear below it. But if you have cost-free government intervention, what you can do is you can push down all of these curves that are exceeding the healthcare threshold. The government chooses, well, if it's costly enough for the government that's down here to push down the threshold, it'll push it down. But what you see is that there's a really sharp switch. The government decides how much it costs for one individual to catch this disease. If it says it's 1150 Hong Kong dollar, then it lets the disease do whatever it wants. It just lets it sweep through society. If it's 1200 Hong Kong dollars, bam, it comes down and stops everybody under this threshold. So there's a really sharp switch in the optimal government policy in the cost parameter. Now, this might actually help to start to explain why governments find it really difficult to decide whether they should do nothing or squash the disease back down into oblivion. Because what we're saying is, well, we're really close to the number where actually you just step a little bit that side and you should do this, you step a little bit that side and you should do that. So actually it's kind of understandable that governments maybe didn't know what they should do. And if you really put numbers in here, which epidemiologists hate to do, but if you just kind of imagine to yourself, well, you know, what would it cost me if I were to catch this disease? How likely am I to die? How much is the cost associated with that? Similarly, for modifying your behavior, you actually end up with numbers that are very much in this ballpark. So COVID is bang on this special value where it's difficult to decide whether you should do anything or not. If you make the disease 10 times as dangerous, it's absolutely obvious you've got to stop it getting around. The solution is clearly a lockdown solution when you get curves like this. 10 times the other way, it's like flu or even less dangerous, you obviously do nothing. But COVID's right on this special threshold. And actually, I'm showing you this here graphically. Maybe we can just look at these curves. This is what happens to the peak of the infection as you turn up the cost of the infection. Basically, if you turn up the cost, you drop off the solution with a high peak, that's do nothing, and you come right down to a lockdown. And you do it very, very suddenly. And where you do it depends on whether the government's intervention is costly or not. How much time have I got, Lehan? Okay. So I'm pretty much done with this first part. Right, what have I done here? I'm sorry if it's a bit mathematical in places, but I think it's maybe nice to get a flavour of roughly what's been done here. We're looking at rational behaviour. That's a technique. That's a big assumption. We're assuming everybody is rationally optimizing their own objective functions. Probably what we should be doing. Whether we are doing it is another question. We've chosen an SIR epidemic model. This is a generic model in epidemiology. It's probably not a very good model for COVID, actually, but it's very generic, and there's lots of other diseases that are SIR epidemic models, so we start there. We say that individuals are selfish, and that generates this Nash equilibrium strategy where you get different trajectories to the disease than if people are not selfish. We've allowed governments to come in and move people around by giving them money. We've worried a little bit about what happens if you have healthcare thresholds. And I haven't really had time to tell you about it, but you can misalign the government and individual interest here. You can say the government cares more, for example, about exceeding healthcare thresholds than we do, and you can see what the outcome of that is. So, right, so the conclusions are, this healthcare threshold is exceeded if there is one, if the maximum cost of intervention is below some critical value. If it's higher, you expect to stay below the healthcare threshold. You get a sharp switch. This critical value is lower for the government than the individuals, and government intervention strategies have got this sharp switch. Right. Okay, so now in the last 5 minutes or so, I'm going to tell you something about this really new bit, which is Nash Neural Networks. So again, we've got a Hamiltonian formulation. We're going to use the same physics, mathematics. I'm writing in a vector form here. I've got the vector of the derivatives of x and I, and I'm writing it in this vector form with the same equations. And I've got the same thing for what the probability of the individuals being susceptible and infected. It's the same equations I had before. And then I just got some notation. The state of the system, which I wrote x is this vector xi. P is your state, the probability of you being susceptible or infected, and this V is the Lagrange multipliers, the fields that we have to solve for. Right, and basically here's the kind of flowchart of what happens. You put in the state, the probabilities, the behavior, and the Lagrange functions. These go into, well, the probabilities and the state go into the F function. This is like the equations of motion, and that appears in the Hamiltonian. And then the probabilities and the behaviour, they go into the utility, and that appears in the Hamiltonian, and the Lagrange bars also appear in the Hamiltonian. The Hamiltonian spits out the derivatives of all these things. And so you can solve this problem. And what we've done is we've done something a bit new, which is where you've got the utility. You know, what I've been telling you so far, I wrote down this nice function with the alpha and beta. Maybe you didn't know what that is. You've all got some way of deciding what you're going to do in the course of this disease, but maybe you don't even know what it is. It's a new, so we're going to call it a neural network. That takes as an input, you know, the probability of you getting infected and what you're doing, and it spits out score. That's what neural networks do. You can feed in some input parameters and they'll spit out an output parameter, which in this case is a score, it's a utility. We don't know what this is, but we're going to treat it like a neural network, and we're going to try and work out how to wire up this neural network to get an accurate mimic of the underlying utility that's driving the dynamics of the system. Because we know that if you know what the utility is, you'll get a Hamiltonian that will give you the trajectory of the system, and we can compare this with the system and say, well, did we get this right or not? If we didn't get it right, we can improve it until it's in good agreement. Right. And you know, I mentioned that there's this tool. I'm not going to have any time to talk about it, but there's a way of taking derivatives through this complicated code that's a neural network with these control theoretic equations. You can basically look for solutions by taking derivatives through the code. I really don't have time to talk about that. What you're doing is you're basically trying to get the dynamics that's coming out of this for the derivative, the time derivatives of susceptible infectives, to agree with some target, which is maybe observations. You know, you observed what's happening in society. In our case, we solve the equations in advance with a known utility, then we hide it, we feed the data into this thing, and we say, can you get the utility back? So what we're doing is actually very similar to these kinds of physics-based approaches, I think I told you, where, you know, if you've got a bouncing ball, you can bung that into a neural network and say what happens next. And you can do it just from a, like, you know, give it the video, and that will give you an empirical prediction of the dynamics. Or you can say this bouncing ball's got Hamiltonian, learn the Hamiltonian and use that to predict the dynamics. We're doing the same thing here, but in a kind of essentially what's an economic context. You can either throw an agnostic neural network at the time course of the disease and say, try and learn, and don't really know what's going on. But for us, we know what's going on. We know the equations. They're just like the equations in physics. We know it's targeting the Nash Neural Network. So we can just plug that in the same way that we plug the equations of physics in on the top line. We can get an empirical predictor of individual preferences. This, by the way, is a very powerful thing. I can look to see what you do and work out what your preferences are. I mean, I think that's got very broad application in economics, much more generally than just in epidemiology. So if you care, this implicit automatic differentiation is a very recent paper by the Google guys, and they're using this a lot in all of their code now. It's amazing. Hamiltonian neural networks, also very recent. What's this? 4 years ago. Again, this is the Google guys. I don't really have time to tell you about how Hamiltonian neural networks work, but I told you basically you learn the Hamiltonian, not do it directly, and basically you get improved. If you learn the Hamiltonian, you get a really good predictor. This is a mass on a spring, the dynamics of the mass on a spring. If you just feed it through an agnostic neural network, you get a poor predictor. So telling it that there's physics there and it needs to find the way of parameterizing the physics is a good way to do it. You can also do it with Lagrangian neural networks. This is what, 3 years ago, same team. That's if you don't have, for those of you that know about physics, there are some problems where it's better to use a Lagrangian than I don't have time to tell you about it. And this is what we're doing basically in pictorial form. Right, and I'm afraid the notation has changed too, so it's really probably not worth me talking you through this, but this is the key point. Embedded in this kind of flow chart, there's this thing. This U is your empirical predictor, and it takes in the state of the system, the probability of you being infected and what you do, and it spits out a score. And we learn this thing by trying to find the optimal solution, the thing that minimizes the cost. And we can do that. And here's some results. So what we do is we feed in the solid line thing is we feed in the numerical solution to this optimal control problem with fixed utility, which is of the form I showed you earlier, like the alpha, a constant alpha, and this quadratic behavioral cost. And we solve it. And then we feed this into a neural network, a Nash Neural Network, and we ask it to infer the utility. And then from that, we generate the dynamics. And the dynamics are these solid little circles here. They're spot on. So what it's done is it's built a utility that exactly mimics the dynamics it's got, if you like, the right utility. And over here, what we've got is the grey curve, it's the quadratic bit of the utility. Remember, it was beta kappa minus kappa star squared. That's a quadratic. It's an upside down quadratic, because it's a minus in front of it. That's the grey line. So we're projecting out just that bit that depends on the behaviour. And what we want to see is this quadratic. And what we're finding are these data points down here. And it's very good at the process of K1, basically the behaviour is all the way to between 1 and 4. It's predicting the utility, the quadratic part of the behavioural utility extremely well. This is very encouraging. I mean, it's a bit of a kind of simple system, maybe, but it's very encouraging that we can do this. We'd like to apply this to real data for diseases and see what we get out. We haven't done that yet. Okay, so that's it. So we've got these Nash Neural Networks that are an empirical predictor for approximating the objective function that does what you do, and we kind of build in structurally the equations that stick it onto a Nash equilibrium. You know, it's got potentially empirical predictive power for human behavior, and there are targets for this beyond epidemiology. I mean, lots of targets, I think, in economics and finance. And that's it. Thank you for your attention.
Yeah, thank you, Matthew, for this wonderful talk. So let's invite people in the audience. Any questions?
One thing that I noticed about the utility equation is you have the cost of differing from the sort of default behavior, the beta times squared.
Yeah.
So that assumes that the difference in behavior is sort of neutral one way or the other.
Yes.
Like is the metric. Have you tried doing experimenting with like an asymmetric difference in behavior function, or do you think it doesn't really make any difference, or it's just an abstraction anyway of it?
Yeah, I think it's a very good comment, and it's true that we just wrote down this quadratic form. Of course, in general, we're used to taking things near equilibrium, near like the natural point, if you like, and then if it's stable there, because by making it quadratic, I ensure that what you do not in the presence of disease is you target this natural K star, and I need to have that quadratic form locally around that to pin me on that result.
Yes.
And you know, very near that, you'd expect it always to be quadratic if it's differentiable. And the question is, how far away do you have to go before it stops being quadratic? And it could be not very far, in which case what you say is a very good something we should consider. My feeling is it probably doesn't make much difference, to be honest. First of all, because usually people are modifying their behavior on the downside, so it's actually it's only the other one half of that side that actually makes any difference.
Sure. Yeah. Can you also explain what the salvage term is?
Yeah, so basically, well, one way of thinking about it is, imagine I knew that in 1 year's time, a vaccine was going to arrive. Basically, you should cut off that integral over your behavior at 1 year, because at that point, a vaccine is going to arrive, and then you don't have to do anything anymore. And so then you put a limit on that integral, and then the salvage term at that point is basically corresponds to the cost of the few people who caught the disease just before the vaccine came in and are recovering after the vaccine came in. And you can calculate it basically because it's just a tail. So it's sort of, if I wave my hands a bit, you can think of it as being associated with the arrival of a vaccine, for example.
Okay, so basically it handles a case where the conditions fundamentally change. So
Yes.
Can't
Yes.
beyond that.
Or for numerical, if you say the conditions never change, actually it's pretty difficult to solve these numerical equations to infinity. For numerical reasons, you always have to cut it. And it's better if you just put in something that gives you roughly what happened when you made that cut, rather than you just cut. So what we do is we cut sufficiently late that this salvage term is basically 0. So we're checking that we can cut in the right place, basically.
Right. Okay, and so you talked about this as a mean field model and you said it again, you have like well-mixed compartments.
Yes.
So then have you looked at having separate compartments, like what happens when you have multiple states multiple, say, countries with, or cities where things are well mixed, but then there's a chance that people
Right.
travel between.
That's a very interesting question. I guess for us, the whole world is well mixed. But you're quite right. You can chop it up into different compartments and have different transmission between those compartments. That's important, particularly if you've got border controls. I think maybe more important is, our compartmental model misses the difference between old people and young people. That's probably a more serious limitation. We've just got one typical kind of person. That's probably not very good. So probably that's what we should fix first, but we could also address this question, probably very interesting. Depends a bit on how you fix up the model of what's happening between the countries, but yeah.
Yeah, that actually is probably even, like in the US, you have different ideas about what the utility function is. You have age, you have immune function, like pre-existing health, and also just different beliefs about people with different beliefs about what their susceptibility is and what the severity is.
Yeah.
Like if you threw in differences in information, there's basically no end to how much more complex it can make this. But yeah.
So I guess our pitch here is that, we didn't really make it very clearly, is that the society should decide on what these costs are. Maybe we can have a referendum on it or something, or the government decides how much does it cost if somebody dies, how much does it cost if you make people stay at home, and you plug it into a theory like this. It probably has to be much more complicated than the one I showed you today, but something like this, and it tells the government what to do, and the government can hold its hands up then and say, it wasn't me, you guys told me what cost to put into this model, and we're just implementing it. So I think from a political perspective, it's actually got a lot of attractive features.
Thanks. Yeah, I'm sure that.
Yeah, maybe a very naive matter. So in reality, so it's possible that the governments can change their policy very quickly. For example, they have different policies in the first month, and after another month they change their policy. And it's also possible that different regions, even in the same country, or even in the same province, they have different policies. So I think in this case, using the model here would capture different dynamics.
Yeah, well, certainly the model, generates the dynamics. It's not possible for governments to change policy overnight, generally speaking, or it's costly to do that. So maybe we should have some time derivatives in here saying that there's a cost associated with changing the controls really fast. We didn't do that. We know how to do it within Hamiltonian mechanics. It's very easy, actually. But yeah, certainly you could have different optimal policies in different provinces that would naturally come out of this kind of methodology.
Yeah. I see. So yeah, so I think so. You're when we use this, so it's the data for the whole country over a very long time. So my point is that it's possible that there are totally different dynamics. So here, if we use one several equations, is possible. It assumes that there is homogeneous.
Yes. Sorry, was that a question? Can you repeat the question?
Yeah, my question is that it's possible that the model could take into account some more detailed features.
Well, sure. This is version 1.0. Super simple because we can solve it. Actually, if you were really going to propose this as a policy tool, you need to have all sorts. You have to have a better epidemiological model underneath. But you can. This is detail almost. It works. So I think something like this could be implemented on an arbitrarily complex epidemiological substrate. Actually, yeah.
Thank you.
Okay, then I've got to ask the question. So I see that in your version that mostly you treat the population as homogeneous.
Yes.
Right? So things in real life, then definitely different people have different preferences and different utility functions.
Yeah.
So is it easy to accommodate this kind of variation?
Yeah, so you can put in, I mean, basically, I think, you know, the obvious way that would manifest itself is young and old. Young and old have very different utilities because they have very different costs associated with catching disease. And that is probably really important, and we ought to have it in here. We could do, very trivially, we have two kinds of populations that are coupled. We haven't done it yet. You know, the honest answer is that we don't know whether the Nash equilibrium survives that. I mean, it's in this simple model, whether it survives that kind of thing, we don't know. Yeah.
And also for the data, on the data side, can you give some simulated data?
That's what we did in the last picture. I'm sure it wasn't clear, but yeah, we did that and it worked.
Yeah. Thank you. Any more questions? Yeah.
Thank you, very nice presentation and this concept. I think here the individual and the government in interaction. So in this model, is it also capturing these extreme case like our government has been like keeping a long time of this aiming serial infection? Is that?
You mean serial as in you
It can be like it's a kind of extreme case of this.
Well, it's a very good point, and I did touch on the fact that the SIR model is probably not a very good model for COVID for precisely that reason, because the recovereds can become susceptible again and catch disease again. So it's a different kind of model. I mean, you know, you can write in epidemiological terms. I mean, that makes a difference, of course, but you can still write down the equations of motion. We haven't done it yet, maybe we should, but yeah, it makes a difference. It makes a big difference. I mean, the results can all be different, basically. But I would like to still focus on the methodology. I mean, I think that's the important thing we've got here is it really doesn't matter actually almost what you put in. I think you could do something like this on it, whatever you choose. Yeah.
Another question is vaccination. I think it's also in a way similar. You have individual decision like you want to take it with it. Vaccination itself has a risk.
Right.
Yeah, and the government one have different assessment of the civil risk or individual have different perception. And also I think individual have the consideration of actually the risk of vaccination or should be applied in the whether your framework can also take this into consideration vaccination as a
yeah, that would probably require a little bit of a modification, but yeah, you want to use something like this. I mean, the decision whether you take an infection or not depends on how costly you think it's going to be for you to get disease, and that's not just now but next week. So you need something like this to decide whether you ought to take a vaccine or not. We haven't done that, but I think you could do that. And I think the other thing that's worth noting in that case is you probably very clearly see again the presence of selfish behaviour, because for a lot of people it doesn't make sense to take that vaccine.
Yeah.
And it might be better for society, but it's not better for you. So you're not going to have a vaccine. So that's another manifestation of these kinds of game theoretic problems you have when you can people's selfish behaviour is better for them than doing what's better for the society as a whole.
Exactly.
Yeah.
That actually brings up what sort of data, if you wanted to fit this model to a real world situation, what data would you need?
Well, you need data between large government interventions because we want endogenous behaviour. In the first instance, we're not going to try and deal with the government intervention. So probably actually countries like in Africa where they didn't really do very much, it's probably pretty good data. Or Sweden, because again, they didn't do much. What you'll see is the endogenous, in the economics language, the natural behaviour of the people coming through, and that's what you need to back out what their preferences are. So we've been looking at those kinds of data sets, and my PhD student who's just started on this stuff. One of the things I've told her to go do is to find those data sets and let's have a look at them.
So you need data without any intervention, and you just need that. You would need with and without.
Well, I think the first thing to do is to see whether this kind of endogenous behaviour at the individual level without government intervention, whether that works. Then when we know whether that works, maybe in African countries or Sweden, then we can start thinking about governments. My intuition is that government's intervention was not driven by anything like this that we can encode maybe so easily in a utility. It's probably very political, related to what's going on in the media and goodness knows what else. It's very difficult to encode in these kinds of things. So whether we can get it or not, I don't know. That's a hard problem. Yeah.
And also you want like the time series for the full pandemic, like you just need. So basically it would need to be reflected as in terms of susceptible, infected, recovered populations or as a time series throughout the course of the pandemic.
Yeah, so because we're mostly solving things numerically, we create essentially a time series. That's how you do things when you solve them numerically. It doesn't just have to be as simple as SIR. You could have et old, S young, I old, I young, as we said, but we haven't done that. And I don't know, things maybe change. But at the moment, we have just the time course of S, a time course of I, a time course of R, and a time course of kappa, what you do. That's what you can change. That's the bit you control. Everything else just comes out the other end. Yeah, thanks for the good question. Very good. Thanks.
Okay, so with that, let's